Hello, this is the demonstration for what I call physics practical. Patent pending, all royalties due to me. Okay. So for this demonstration, you're going to use this piece here. This piece is three LEDs with a positive being the red and a negative wire on here. And so what you're going to do is you're going to take these here, just bring it in the front for everybody to see. And for the you're going to positive and negative wire. Just kind of like this. Okay. Now if they're all hooked up properly, you can start to turn on or voltage generator to make sure that everything stays low power because you want the effect of each of the lights turning on in sequence. Okay. Now we're going to start with the outreach type demonstration. So for a general audience for outreach, what you're going to want to start with is you're going to show your patent pending physics traffic light, and you're going to tell people what you're going to do is you're going to increase the power to this light. You want to ask them what they think is going to occur. Get a couple answers, field a couple of them, see what they say. If anybody guesses right, you can probably just move on from there and start actually turning it. So what you're going to want to do is start turning up the power on this. This voltage generator has a coarse and a fine. You want to make sure you don't turn up the power too much. Anything past 2.8 volts should be really unnecessary. So if you're not getting all of the lights turning on, as you're getting up to like 2.8 or even 3 volts, don't try not to push it that high, please. Just stop and have somebody come look, like Kyle, come look and try and fix it for you. Because if you turn it up too high, you're going to end up burning out these top balls, and then it's going to, the demo's going to be out of commission, and we'll have to repair it. So please be careful with the voltages that you put in. So what I'm going to do is I'm going to turn this up, and the voltages you kind of want to look for to start is the red bulb turns on at about 1.7 volts, like very, very dimly. So if you kind of get your coarse voltage just about up there, and then you can start to turn the fine voltage, and that'll get you the effective. So I'm going to start turning this fine voltage meter, right? And you should be able to see the red, and then the green, and then the blue. They all come on in sequence. Red, green, blue. It's going to be a little hard for the camera to pick that up, but you can see them. I'm going to move this a little closer so you can see the effect a little bit better. So one last time. As you can see, you get one, the red one, and then the green bulb, and then the blue bulb. And then, that's at 2.9, so you really don't need to turn it any higher than that. Then just go ahead and turn it back down. Okay? So, showing that effect, which it'll be pretty apparent for class, you can then ask them, why did this happen? Why the balls turn on and down? Some people might say something like order of the balls. They might say something like just like how they're generally worked. And the correct answer, of course, is the color of the balls. So I want to explain that each of these balls is a specific color. One's red, one's green, blue, fairly apparently. But the light that they give off is that specific wavelength. So all lights have a wavelength that they have. Red has a much larger wavelength. So the space between the waves is very big. And that means that red doesn't need a lot of energy. It's a little bit chill. Okay. And then green is a little bit more it's a little bit smaller of a wavelength, and blue is even smaller. And so because it's a smaller wavelength, it needs more energy to produce that blue light. That's why things like, you have visible light, which goes from like red to purple. Then you have like infrared, which is even less energy. Then you have ultraviolet, which is even more energy, right? Those are just the spacings on the wavelengths. And the reason for this is because each wavelength has a specific amount of energy that needs to be produced. And so that's why as you increase the power, first the red one shows up because that's the lowest energy, and then the green because it's the next, and then the blue because they have energies ranging in that order. And that's where I would stop for the kind of general outreach type demo. That's a good explanation, and you'll get a nice effect for people to see. Okay, now for the physics classroom demo, there's actually a lot of interesting physics and science that can actually go on. So as we saw, each of those turned on in order. Now, for those of us taking like an intro quantum class or something like that, we'll know that each wavelength has a specific energy and that they can be related. The way that these can be related, importantly, is using an equation, right? Stored energy is equal to Planck's constant times the speed of light over what is it? Okay, so we can use this relation to relate the energy, the voltage here, to the wavelength that we saw here. We can do this by saying that the energy is equal to the electron volts. So this is just the charge of the electron, and this voltage would be the voltage that we see in our voltage generator. From this, we can then state that the voltage here is equal to H bar or HC over the charge times 1 over N. Now this final equation, this voltage equation, is important here because what you can do is you can create a graph. You can create a graph of voltage on the x-axis and 1 over lambda on the y-axis. This allows us to do. This allows us to create, which I'm going to do. I actually have a Excel spreadsheet will be provided to roll help. Where what you're going to want to do from the classroom demo is you're going to want to go through and report what voltage each of these lights turns on. So I'll start with the red. Turn it up and we'll say it's like 1.94, at least nice and bright. So 1.9, 1. And then we can turn it up even more. This green one, say like 2.25. And then we can turn it up even more. You see that blue. So it's like 2.16. Okay? So 1.91, 2.24, and 2.68. Okay? Now this here is your estimated Planck's constant, right? That's all this spreadsheet is doing, it's graphing that voltage and 1 over lambda graph that I just read. This is going to be our slope, which I've referred here, just by 1 over lambda volts to get the slope. And so from this slope, using that equation that I wrote earlier, we can solve for Planck's constant. And the value that you're going to get, I got 6.001 times 10 to the negative 31st. It'll be off by an order of magnitude or two. And that's because, these wavelengths aren't the most exact. LEDs have a range of wavelengths that they actually produce. And so because of that, you're not going to get an exact wavelength. Your your mileage could vary on how accurate, your exact turn-on voltage is. Lower would probably be better. But from this, you get a rough estimate of Planck constant. And this is something physical that the students can kind of look at and be like, oh, this is one way that, you can derive Planck's constant. It may not be the way that it was done in the past, but it is something that they can latch onto and be like, oh, this is what Planck's constant is. This is how we get it. This is an experimental only method.